Welcome to my lecture on exponential growth and decay. Okay. And this is on section 6.5 of your textbook. So we're going to go over a couple examples in which you see exponential growth or decay. And here's my first example, and it's on population. Populations grow proportionately to their size. So if we have a 10% increase in growth, if the size of the town is 100 individuals, the next after a year, and assuming that the growth rate is per year, 10% more would be 110. Whereas if it's 1,000, the population the next year would be 1,100 after a 10% increase. So we're going to assume populations grow proportionately to their size. And what this says, that if Y is the population of a town, then its growth of Y is nothing more than dy dt. That's the rate at which Y grows with respect to time. And you said it's proportional, or we said it's proportional to its size or population size. And the population size is nothing more than Y itself. So dy dt is equal to k times p, the population size. And so this is what's called a differential equation, okay? And you don't know that yet, but it's a separable differential equation. And what I mean by separable is that we're going to treat dy dt as a fraction. Okay, so we're going to treat this like a fraction. And that's what separating means here. Okay. So if I do this, I have dy over k, dividing both sides by k, is equal to dt times p. And excuse me, one thing I'd like to correct here is that the population size p, well, that's given by y here. Okay, so I can replace p by y. Okay, and this is our equation. So this is now, the equation is separated, so now we take the antiderivative. Okay, so I have this integral of 1 over k times y dy is equal to this integral of dt. Well, we can now anti-differentiate each side, and this is the same as 1 times dt. This left-hand side is going to be 1 over k times the antiderivative of 1 over y dy. The right-hand side is going to be equal to a constant, okay? So I'm going to put the is going to be equal to a constant, but also is going to be equal to t plus a constant. The derivative of t is 1, the derivative of constant is 0. Okay, now on this left-hand side, I'm going to get 1 over k times this ln of the absolute value of y is equal to t plus c, and I'm going to solve for y. Okay, so we get ln of the absolute value of y is equal to k times t plus kc. Okay, then I'm going to exponentiate to get y. So y is going to be this exponential of kt plus kc, and this is going to be equal to e to the kc times e to the kt, and this is a constant right here. So I'm going to call that a0, that e to the kc times e to the kt, and that is how my population grows. Now, the population at time 0, that's just y of 0, so we plug that in. That's going to be a0 times e to the k times 0, and that's just equal to a0. So a0, this is the population at time 0. Some people call that the starting population. Now, let's do just a brief example. Suppose the size of a town is 100,000, and the growth rate is 2%. Okay, and that's equal to 0.02. So we have to express everything in terms of a decimal. And the question is this: what is the population of the town in 10 years? And you'd use nothing more than this equation. Y is equal to a0 times e to the kt, and we're just going to plug in 100,000 for a0 times e to the 0.02t. Then to figure out the population in 10 years, we figure out that y 10 years from now is going to be 100,000 times e to the 0.02 times 10. And when you do this calculation, you get 122 and 140. Okay, so that's the approximate population of this town in 10 years. Okay, let me give you another example. Okay, so it says that this this bismuth 210, which is an isotope, has a half-life of 5 days. And it says if we have 800 milligrams, find a formula for the remaining amount. Okay, so this decays at a rate proportional to its size. Okay, so every 5 days we get half as much as we originally started with, and that's why it's proportional to its original starting size. So we view this as the same relationship that here the amount of mass at time t, and I'm going to call this m of t, is all of this. Well, it has the proportionality relationship that its rate of change is equal to k times m. And that's exactly the same equation we had before. So the mass, just by doing the same differential equation, is going to be equal to m0 times e to the kt. We're told that m0 is equal to 800 milligrams. So this is going to be 800 times e to the kt. What we're not told is the value of k. So what is the value of k? Well, we do know in 5 days we have 400 milligrams. So we have 400 had better be equal to the amount prescribed by the equation. So this is going to be e to the k times 5. And now we're going to just write out this equation and solve for k. Okay, so we divide both sides by 800, we get 1/2. Okay, 1/2 is equal to e to the k times 5, and then we're going to get the ln of 1/2 is equal to 5k, so k is going to be ln of 1/2 divided by 5, and that is approximately minus 0.138. So our equation for our mass is going to be 800 times e to the minus 0.138 t, where t is in days. And if we were to graph this equation, its rough sketch would look like this. Here's going to be 800. That's its starting amount at time 0. And it eventually goes down and down and down, and it has an exponential decay. Okay, and I encourage you to sketch this graph on your own time. Okay, and remember when our curve sketching for exponential growth and decay, this is consistent with it. It limits to a value of 0. Now, here's another question. How long until there's only 1 milligram remaining? Well, this is just algebra. So we set the mass equal to 1 milligram, and the mass is given by 800 times e to the minus 0.138 times t is equal to 1, and we're going to solve for t. Okay, so we get e to the minus 0.138. T is going to be 1 over 800. Then to solve for the next part, we're going to take the log of both sides. So we're going to get minus 0.138 t is equal to this ln of 1 over 800. T is going to be this ln of 1 over 800 divided by minus 0.138, and that's approximately 48 days. Okay, and I rounded there, so you might get a slightly different answer, but it should be pretty close. Okay. Now I'm going to go over an example of compound interest next. Okay. And here's your example from continuously compounding interest. Okay. And it says this. It says if $1,000 is invested at 5% interest, compounded n times per year, how much money will you have after t years? Well, the equation that describes your amount of money, okay, with n compoundings, so your amount of money is given by this equation. It's your initial amount times 1 plus r over n to the nt. And here's going to be your question. What if the money is continuously compounded? Well, all this is saying is that the amount of money that you'll have, there's not a finite number of compounding, so let's take this limit as n goes to infinity of a0 times 1 plus r over n to the nt. And because a0 is a constant, we can take that outside. We can also do this. So I'm going to write a0 times this limit as n goes to infinity of 1 plus r over n But I'm going to put the exponent, I'm going to make it slightly different. I'm going to make it as n over r, but then I'm going to put it to the RT power. And using the law of exponents, those two would multiply, and I just get NT. So the exponents would be the same. Now, if I let z equal n if I let z, or excuse me, m, if I let m, my apologies, if I let m equal to n over r, then this equation is going to read as a0 times this limit as m goes to infinity, but since r is greater than 0, n going to infinity means m goes to infinity. So I'm going to have this limit as m goes to infinity of 1 plus, we have m is n over r, and inside this we have r over n, so that's 1 over m to the power of m raised to the RT power. This is the definition of E. Okay? And so I wind up with A0 times E to the RT. And so this is A0 times E to the RT. And the point is that if I have continuously compounding interest, the equation that describes it is given by this. That is continuously compounding interest. So let's ask a question about continuously compounding interest. If you invest $1,000 continuously compounded at 5% interest, how much money will you have in 3 years? And well, to answer this, we just plug in A of t is the initial amount, which is 1,000 times e to the 0.05 times t, and I want to find out after 3 years. So this is going to be 1,000 times e to the 0.05 times 3, and that will be approximately 1161.8. Okay. And you might ask another question. How long until it doubles? And for it to double, you'd have to get $2,000 from your starting amount of 1,000, hence the doubling, times e to the 0.05 times t. Divide both sides by 1,000, and you're going to get that 2 is equal to e to the 0.05 times t, and you're going to get ln f2 is equal to 0.05 times t, and then you can solve for t. T is this ln of 2 divided by 0.05, and that's approximately 13.8 years. Okay, so you can make some money if you have enough time, is what that's saying. Okay, now there's some other questions in this chapter on cooling and Newton's law of cooling. I'm going to let you read that and look at that. That's all that I have for this lecture.